All right, let's go ahead and take a look at Unit 4 electron notes. So this is the last unit before the semester is over. We'll come back in January and we'll start off with Unit 5, which would be the periodic table. All right, so I'm going to go ahead and make sure you write your name over here at the top. And the beginning starts off with just a little bit of a reminder of what we talked about last unit in chapter or unit 3 when it came to the atom itself. It started off with the history of the atom and the model and how it changed and evolved. Remember, why did the atom model evolve so much? Was mainly because of newer technology. As we advance in technology, we were able to discover new things out there. Okay, so Thomson, Rutherford, Bohr, and then the quantum mechanics model, which is what we use currently. That's where we're at. Okay, even Bohr's model was not perfect. So let's go ahead and just kind of write a little review of what we know or what we remember from previous unit. Thomson discovered the electron and proved Dalton wrong because atoms can be divided or divisible. Right? We have what we call subatomic particles, the protons, the electrons, and the neutrons. Now, yes, they're not just a hard, solid marble. They're made up of subatomic particles, and we can divide it if necessary, but it's no longer going to be that atom. It's going to be something different. Okay, so let's keep going. Rutherford, he came along, and I know there's not a lot of space, so I'll do it in a different color. He added the nucleus. Right? He found this because of that, figured out that the nucleus was a hard center inside of that atom. And then after that, we ended up with our Bohr model, and he took it up another notch and he added orbits to Rutherford model. Right? And then after that, and I'm so sorry, I wrote Rutherford, but it was really Chadwick's model that he added, right? Because Chadwick discovered the nucleus, and after that came Bohr. So I'm going to go ahead and change that to Chadwick. And then we got the newest model that we currently use, and we utilize this one. The quantum mechanics model added sub-levels and energy levels. Believe me, at first, this is going to be very confusing. Hopefully, you've already watched those other notes, the video notes. Okay? Again, we're going to do these notes. It's still probably going to be confusing. We've got homework. You still may be a little bit confused. We have videos to watch. This concept is very confusing because it's not something tangible that you can hold on to or look or calculate or figure out. It's a model. And this model is so tiny, small that there's, it's not like if you can actually see it. That's what makes it so hard to figure out. Okay. The other thing when it comes to our energy levels and sub-levels here is that they're not perfect orbits. We don't orbit, our electrons don't perfectly orbit in circles, okay? Our energy levels are not in perfect circles, and that's the key thing here, is that we need to toss that theory that you have out of your mind, that we have the center nucleus and then you have the energy levels and the electrons orbit it. The electrons don't orbit around like that planetary model, okay, that you've traditionally known of. It actually orbits, or it jumps from different energy levels, and it does it in these weird shapes. They're dumbbell shapes. They almost look like raindrops or teardrop shapes and sphere shapes and donut shapes. They're actually shapes, and they're within that shape, jumping within that shape to different energy levels is what the electrons are doing. So make sure that we know that these energy levels are not perfect circles. Right? This is what we've been taught or told, and we assume, but it's not, that's not correct. Not at all. All right, so let's go ahead and begin with our notes now. It says here, the quantum mechanics model, where are the electrons? Okay, so it says here, a region around, or the principal energy levels. Okay, the electrons live in certain energy levels, okay? And the energy levels where they live in, this is where they live in, is a region around the nucleus of an atom where the electrons are likely to be moving. And I'm going to go ahead and put in parentheses 90% of the time. Okay? Believe me, we've tried to pinpoint an electron. Oh, this is where it's at. And when we go to look to see it at that moment, it's not there. Most of the time, it's not there when we try to find those electrons. So what we know is a probability of where the electron should be at. Unfortunately, though, because he jumps from place to place, and he doesn't necessarily move like from here to here. He literally jumps from here, and then an instant later he's over here, and we're like, how did you get over there? You didn't follow the path. You didn't go a certain way. It just literally jumps from here to here, and it's very hard and very difficult to find and pinpoint down an actual electron. Okay, let's keep going. The principal energy levels are assigned values in order of increasing energy. Okay, the average distance of the electron from the nucleus increases with increasing energy levels, one being the closest energy level to the nucleus. Okay, next one here, it says within each principal level, or each principal energy level, that's the abbreviation of EL, energy level, the electrons occupy energy levels or subatomic energy levels. Energy levels. Okay, let's keep going. I know this is abstract thinking and some weird stuff here. Now, the energy sublevels, the number of energy sublevels is the same as the number of energy levels. The sublevels are labeled as S, P, D, and F. according to the atom's orbitals, or the shapes of the atom's orbitals. So we have what we call an S shape, which is a sphere. We have a P shape, which is, it looks kind of like the infinity sign, or two teardrops. And then we have the D sublevel, which looks kind of like a flower. Okay, and then we have the F energy level, which looks like two of these flowers put together. Okay, atomic orbitals. Atomic orbitals represent the electron probability. When we say probability, we're just meaning about 90% of the time. Okay? They're called probability clouds of an atom's electrons. Each orbital may contain at most 2 electrons. Each energy level may contain at most 1 s orbital, 3 p orbitals, 5 d orbitals, and 7 f orbitals. I know this is still crazy, but hopefully it will make sense later. Again, you're going to have to start asking those questions. It may not be the first or second time we have our meeting, but give it some time. After a while, please start asking the questions, okay? Let's go ahead and let's look at this. Energy level 1, 2, 3, 4. Energy level 1, the number of sublevels it contains is I'm going to put EL here for energy levels. 1 s. Number of orbitals, 1. Number of electrons, 2. Because the s can only contain 2. Okay? This is an important chart right here. Energy level 2 can have 2, which is an S and a P. Number of orbitals is 4, and the number of electrons maxed out is 8. The next one, level 3, contains an S, could contain also a P, and it could have a D. Okay? Number of orbitals, 9 max. The number of electrons, 18. On the 4th energy level, okay, the 4th one, can contain an S, can also have a P, could also have a D and an F, and a max of orbitals 16. And in those max orbitals of 16, each one can contain 2 electrons. So 16 times 2 equals a max of 32 actual electrons in there. Okay? All right. So, again, we're going to come back to this. We're going to need to understand this chart later on more. Let's keep going. Now, hopefully, if you've already watched your video notes, then you've already seen a little bit or heard some of these words. Okay? So, electron configuration, really important. Okay? It's important when it comes to how they're going to combine and form compounds. It's important on how it's going to react with something else, how volatile it's going to be. The electron configuration is also so important that it tells me whether or not, if my electrons are spinning in opposite directions, and all of those orbitals or those spaces are full, it can cause that metal to become magnetized. I mean, there's a lot to go along with this electron configuration, believe it or not. Let's keep going. A shorthand, what is the electron configuration? It's a shorthand method of writing quantum numbers to represent the location of every electron in an atom. Now, there's different rules. We have three main rules pretty much that we have to follow and abide by. We have the Aufbau rule, principle, the Pauli exclusion principle, and the Hans rule. Okay, so all three rules have to be abided by at the same time. We can't just let just one go, or maybe this one, and all three have to be abided by every rule at the same time. So the Aufbau principle, electrons enter orbitals of lower energy first. And there's an actual order. The order goes here. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. There's an actual order. And the electrons have to fill up this one, then this one, then this one, then this one, then this one, before it can jump over here. Now you use the periodic table, and I'm going to teach you how to use the periodic table. We thought that that periodic table only gave us the atomic mass, or it only told us the atomic number, but the periodic table tells me so much more. I can figure out the number of protons, the number of electrons, the number of neutrons. I can also use that to figure out the amount of mass in a mole, in that molar mass. Now, believe it or not, this periodic table can also tell you where those electrons are going to be and in what order that it's going to fill the energy levels in. That's how much information a periodic table contains. Oh, believe me, there's a lot more we're going to learn about next unit also. This, you have two choices. I will teach you a shorthand method on how to do this, or you memorize this order. And actually, this is not even the full order. It keeps going. Okay? It keeps going. There's so much. Now, me personally, I'm sorry, but I can't memorize that order at all. But I do know a shorthand method that I use personally. And with that, I can figure out all of this and where and the probability of the order of what energy levels the electrons are going to fill. Okay, so I will definitely teach that to y'all. The next one, the Pauli exclusion principle. It says here, though, no more than 2 electrons can occupy the same orbital, and they must be spinning in opposite directions. Okay, one goes up, the other must go down. And this helps create magnetisms, okay, metals to be magnetized. Hans rule, it says here, orbitals of equal energy must each have 1 electron with the same spin before any orbitals is occupied by a second electron. Okay, and so we'll definitely get into that as well some more. Okay, so it says here, how is it written? So for an example, if we want to talk about, or the question asks you, go ahead and write the electron configuration for a certain element, it's going to look something like this. A number, a letter, a number. A number, a letter, a number. A number, a letter, and a number. And it's going to continue until all of the electrons are used up. So the large number is the energy level. The small letter behind that number is the sublevel. And that little superscript up here, okay, that little number at the top is the number of electrons. So the large number, the letter, and that little bitty number up there at the top is the number of electrons. Now, what element from the periodic table is this? Let me go grab my periodic table. And let's talk about how can I figure out what element. If that little number is the number of electrons, let's count it up. 2, 2, and 6. So 2 plus 2 is 4. 4 plus 6 equals 10 electrons. Because if that little number is the number of electrons, let's count up all the electrons to see the number of electrons. And what does the periodic table tell me? First thing is, I know that all atoms are considered to be electrically neutral. And so in that case then, if the atomic number at the top is the proton number, and my atom is considered to be electrically neutral, then that also tells me the number of electrons. Who has 10 electrons? Well, that person or that element must have 10 protons. That proton number is the atomic number. Who is number 10? Neon. So this right here is the electron configuration written for neon. Look at that. Pretty cool. So how do you check, it says? Well, let's go ahead and let's look at this one. Let's practice and try it again. 2 plus 2 plus 10 plus 1. So 2 plus 2 is 4. 4 plus 6 is 10. 10 plus 1 equals 11 electrons. You agree with me? 11 electrons? Count them up. Now, go to the periodic table. Let's check it. Who is number 11? Na, sodium. So the total of subscripts equals the number of electrons, which equals the number of protons, comma, which so the subscript equals the number of electrons, which equals the number of proton, which is the atomic number, right? And why does the electrons equal the protons? Because atoms are considered to be electrically neutral. It says here, last part of electron configuration identifies the element on that table, right? We just saw it. One more time. We just saw how we added up all the electrons, and we found that that's the electron number, which is the same as the proton number, which is the same as the atomic number. But this is the neat thing. The last part of the electron configuration identifies the location of the element on the table. So the last part of it, of the electron configuration, identifies the location on the periodic table. I mean, this is right here. This is just blows my mind away. And I just do not understand how people do not see that this periodic table that we have is so freaking awesome. So let's look at this. The last one, which is 3s1. So I'm going to put that over here. 3s1, right? That's the last part of this electron configuration. 3 stands for the third energy level. The S stands for the sublevel, and the 1 stands for the first square. What do you mean, Miss Munson? Oh my goodness, we're going to come back to this after we do, it's kind of like this little foldable / periodic table thing, and it's just going to be like amazing. I don't know about y'all, but it blows my mind knowing how I can read the periodic table in such another way that most other people can't read or do not know how to read it. So we're going to come back to this, but we're going to come back to this when we cut up and we color our periodic table. We're going to have to do that first so that way you can understand this better. Okay, so let's keep going, and we're still practicing electron configuration. So examples, sulfur. Let's find sulfur on the periodic table. It's a non-metal. It's over here. His number is 16. That means he has 16 electrons. Well, what was his configuration going to look like? Well, here's the order, right? Again, you don't have the shorthand method on how to do it, so you're going to have to use this order. 1s. How many can the S have? S level can only have a certain number. Go to the front page. S's, right, have 2 electrons. The next one is 2s2. Where do I get it? I'm up here. 2s, 2 goes behind because it max is 2 electrons in the S energy level, okay, or the sublevel. What's the third one? Third one is 2p. Okay, now we have 16 electrons. So far we've used 4. So we have 12 electrons left that we can use. Okay. Let's come over here. This energy level, the second energy level, can contain an S and a P. Okay, which are 4 orbitals, which can contain a max of 8 electrons. Okay, if out of these 8 electrons, I'm telling you right now, the S can only contain 2. The S can only hold 2. S's can only hold 2 electrons. P's can hold, well, how many can P's hold? If this level right here has an S and a P and the max is 8, let's take away the 2 that belong to the S. How many's left over? 6 electrons. Okay? So what is the max that this sublevel, that 2p can hold? This p can only hold 6 electrons. Why is it not 8, Miss Munson? Because you have 8 over here. Wait a minute, I have an S and a P. And S's, look right here, can only hold 2 electrons. So 8 take away 2 equals 6 left over. Those 6 are going to go into the P's. Okay? So where are we at? 6, 7, 8, 9, 10. I still have 6 more electrons that I need to put into like a seat. Imagine this is a bus. Okay? And the first seat in the bus is the 1S. And you tell 2 electrons, come on 2. Where y'all 2 are going to sit here on this first seat. The next seat is an S seat, right? The second row, okay? And on the second row, it's going to contain, again, only has 2 spots, so I can only have 2 electrons. Come on 2 electrons into this bus. Now, this bus is a weird shaped bus because the third row is still part of the second energy level. That's what the 2 is for, okay? But it's a P, and on this P row, it can only contain or hold 6. So we tell all 6, come on 6, we need 6 electrons. 16 is the max that sulfur holds. or that's how many he has. So I still have more spaces. So I need to keep going until I run out of electrons. But we have to go in order from the first row of the bus, and then the next row on the bus, and then the next row on the bus. All the seats on the bus have to be filled by the first, second, third, fourth, fifth. We can't have those kids that go into the bus, and you know who those kids are. And where do they go? They go all the way to the back. Why are you going all the way to the back of the bus? When we fill this bus up here with electrons, we fill the first seat first, and then the second seat, and then the third row, and then the fourth row. And that's how we fill it up. We don't just jump to the back of the bus. Why are you wasting that energy? You wonder why they don't go to the back of the bus, these electrons? Because they're smart. Okay? The smart ones are going to sit in the front of the bus. Why are they going to walk all the way to the back of the bus and waste all of that energy? No, sit right here on the first row, right here behind the bus driver. There's nothing wrong with sitting right here behind the bus driver. You don't have to walk that far. You don't have to use that much energy. And that's what the electrons are doing. Electrons try to use the least amount of energy possible. So what does it say over here? We did the 1s, the 2s, the 2p, a 3s. So the next one is going to be a 3s. Again, how many electrons can fit in an S? 2. 2, 4, 10, 12. Oh man, we still have 4 more to go. Who's after them? 3p. Okay, how many can fit in the P? Well, we've already talked about that, right? We know how many can fit into the P. We can have, what? 6, right? But wait a minute. We only have 16 electrons. 2 plus 2 is 4. 4 plus 6 is 10. Plus 2 more is 12. 16 take away 12 equals 4 left over. I cannot put a 6 here. I mean, what? Am I going to just make believe and have to? No, I only have 4 more electrons, so I fit 4. I can't fit more, but I could fit less. Okay? So I stop there. I have no more electrons, so 4 take away 4 equals 0. I'm done. Orbital diagram. Now this is called the electron configurations with the letters and the numbers like this. But orbital diagram, we haven't talked about that yet. An orbital diagram is what over here, the Pauli exclusion says that the electrons must spin in opposite directions, okay, when they're in their seat on the bus. And so the orbital diagram for the sulfur is going to look like this. And this is going to represent the 1s2. Or we could just call it the 1s. We don't say the number behind it, actually. Not in chemistry class. The next one is a 2s.